Hi, in this video, we want to start taking a look at quadratic forms. All right, so remember, a quadratic form is where we have a vector transpose times a matrix times the vector itself. And in most of the time, we're going to be talking about the matrix being symmetric. All right, so let's go ahead and dig in. Theorem 5.2, if y is a normal vector, mean mu and covariance sigma, A is a p by p constant matrix, then the covariance of y transpose a y, so this is the quadratic form of a and y, this is going to be equal to 2 times sigma a times mu. All right, so how do we prove this? Well, what do? We're going to use the definition of covariance. Not surprising, right? Okay, so remember that when I look at this, y transpose is 1 by p, a is p by p, and y is p by 1. When I do this multiplication, I get a 1 by 1. 1 by 1 is better known as a scalar. All right, so this is going to be easy peasy lemon squeezy. What we're going to do is take the definition of covariance, which is just the product of the term minus its expected value. So here we've got the two things. Okay, so now what I'm going to do, I'm going to use a formula that we had previously, and I'm going to replace this with the trace of a sigma, and then the quadratic form of mu and a. All right, so this part gets replaced. All right, so now what I'm going to do is I look at this and I see that, I mean, it would be really natural if I have y minus mu here, then instead of having y's and mu's floating around, I would like y minus mu to be appearing in this formula. All right, so what I'm going to do, I'm going to make this substitution. I'm going to take the quadratic form of a and y, I'm going to replace it with the quadratic form of y minus its mean with a, and then the other stuff that makes it so that we have equality. All right, now, how did I get this equality? What did I do? Well, I said that I wanted y minus mu in my formula. So I started here, I expanded out the matrix multiplication, and then I rearranged the terms around the equal sign, and boom, I get this. So what I did was I took this, I expanded it out, expanded the matrix multiplication, and that gave me this term and this term over with this. Okay, so now what we're going to do is when I make the substitution, I can see that I get this part. Now here, realize that I've got this going on. Oh, sorry, I have this. Let me look. Make sure I have everything accounted for. I might be missing a 2 in there. I think I might be missing a 2. All right, now it works out in the end. So here we've got all this business going on, and you'll notice that we get some cancellation going on, which is all right. And so then I've got all of this going on. I'm going to go through and distribute this y minus mu all the way through. Now, when I do that, you'll notice that I get y minus mu times its transpose. This is going to be important in a moment. And then I get y minus mu times its transpose. And then we get y minus mu. Okay, well, when I take the expected values, remember expected value is a linear operation. So then I get expected value, expected value, expected value. All right, so here, that's going to be equal to 0. Well, hopefully we know that. Now this, well, that's the definition of sigma. Boom, got that. Now here, and here's something that you may not have seen yet so far, but this corresponds to third moment. And so third moment for normal distribution is equal to 0. Therefore, we know that this expected value is 0. Okay, so that cancels out, the trace cancels out. We're just left with the sigma here. So I get 2 sigma a mu. Boom, we get the result. All right, so now let's say that B is a K by P constant matrix, and Y is normally distributed with mu and sigma. A is P by P constant. Then the covariance of BY with the quadratic form of Y and A, then the covariance is going to be equal to 2B sigma A mu. So the difference here is that when I put a B in front of the first Y, I get a B in front of the covariance. Okay, well, how do we do this? Same thing we did before. So I start like I did, take the definition of covariance. Now I notice that I've got a B and I've got a B. And we can remember on expected values, we can factor out a B. So here I factor out the B. So now I've got B times a vector, B times a vector. I can factor again. So when I do that, I see that I get B times Y minus its expected value. Well, B is a constant. So I can go ahead and factor out the B out of that expected value. So I factored it all the way out. Now I recognize that, hey, this is exactly the same thing we had in the previous theorem. So boom, we get the result. And that's a multiplication symbol right there. So we get it. Easy peasy, lemon squeezy. All right, so now if we let V be Yx, so it's a partition vector. A is Q by P constant, and the expected value of V is the stacked expected values, and the covariance is exactly what we would want it to be. Then the expected value of the bilinear form of x, a, y is equal to the trace of a covariance y and x plus the bilinear form of expected value x, a expected value y. All right, so let's take the proof. First and foremost, what do we get when we take a bilinear? Remember, that's a vector transpose matrix vector. So that ends up being a 1-by-1, better known as, you guessed it, a scalar. Okay, so this is a scalar. Well, a scalar is just a 1-by-1 matrix. So if I take its trace, I'm adding up along the diagonal, I take a trace. There's only one entry, so it's equal to its own trace. Okay, so this is equal to its own trace. Now, think about this for a moment. If I'm taking a trace, inside the trace operation, I can switch the order. Matrices commute inside the trace operation. So I can change it to AY, then X transpose. I'm just switching the order of AY and X. Okay, so if I take the expected value of both sides, the expected value of the bilinear form is equal to the expected value of the trace of AY times X transpose. All right, now, trace is an addition operation, and expected value is a linear operation, which means I can pull the expected value on the inside. All right, so then I have the expected value of AY X transpose. Well, A is a constant matrix. A is a constant matrix means I can factor out of an expected value. Boom. This is getting good. This is fun. All right, so now we have the expected value of Y times X transpose. Now, if you remember, we have a formula from chapter 3. It's line 334, and that tells us that the expected value of Y times X transpose is covariance YX, and then I have the corresponding expected values in this position. So remember, it's not just the expected values, it's the covariance plus the product of the expected values. Okay, so now I replace this with that bad boy. Okay, so now I've got A times covariance times the expected values being multiplied. All right, well, what can I do? I can distribute the A, and then remember, I'm doing addition. If I'm doing trace, I'm doing addition. So that means I can, the trace of addition is the addition of trace. Okay, so, because of it's all adding up and I can switch the order of addition all I want, this is the same as the trace of A covariance and the trace of A times the product of the expected values. Okay, well, what do we do next? Well, you know what? If you think about it, when I started out, I had X transpose AY. So it would be more natural to have this in the same order as I have this. So I'm going to switch the order just like I did when I first started out. All right, so now, what type of thing is this? Well, that's once again, that's a bilinear form. It's a 1-by-1 scalar, which means the trace is equal to itself. Boom, I've got that. And this stays the same. I can't simplify that at all. So that's good. All right, so now let's go ahead and let's use this. All right, so one thing that's nice about these matrix formulas is that they make a lot of these calculations, from our stat theory courses, a heck of a lot easier. I mean, they are a lot easier if we do it this way. So if I look at this, if I've got, the covariance of X and Y, the estimated covariance, then I've got this formula. Now I could go through and I can say that X is equal to this vector, which corresponds to my sample. Y corresponds to, or Y vector corresponds to the sample Y. Now here we're saying that we have the X's are independent, identically distributed. The Y's are independent, identically distributed. So the expected value of the vector is going to be the expected value of the X variable times the J vector. The expected value of the Y vector will be the J vector times the expected value of individual Y. Now, let's think about the covariance. Well, independent. So I know that the covariance on X is going to be something times the identity. All right, so it's going to be the variance of X times the identity matrix. Because of independence, the off diagonal is 0. Same thing for the Y. So I know that I've got this going on. All right, and and to be working this out, we're going to from the independence assumption, we can go ahead and just put down the identity matrix in the covariance partition matrix position. Okay, now let's look at this version of the covariance estimate. All right, so here I can see that that's a dot product between X and B. And now this, if I think about it for a moment, I can represent X bar as 1/n times the dot product between X and the J vector. Y bar is 1/n times the dot product of the J vector times Y. And so we go ahead and just write them out this way. All right, so now I've got everything in terms of vectors and scalars. So all my X's are in vectors, all my Y's are in vectors. All right, well, if I think about this, I can go ahead and rewrite this so that n's cancel out, this 1/n comes out. So I get X transpose Y, or sorry, X transpose J, J transpose Y. All right, so the J times J transpose, if you remember, that's going to be capital J. That's a matrix with all ones on it. All right, and that's how I get this. And remember, all right, so when I get to here, I see that I've got X transpose a matrix and Y. So I'm looking to do some factoring at this point. So I go ahead and I put an I between the X and Y over here. Remember, I doesn't change any multiplication, so I can insert it wherever I want for multiplication, and it doesn't change anything. Once I get to this format, I can factor an X on the left, I can factor a Y on the right, and I get this. And that's looking pretty good, because now I've got in the formula from the previous theorem. So what I can do, so I've got X on the left, Y on the right, and a matrix in the middle, and it's symmetric, so I have a bilinear form. So if I look up here, I can use this formula where A is that thing in the middle. And then this will be the expected value of X times the J vector. This will be the expected value of Y times the J vector. And it's just a plug and chug. It's beautiful. It's beautiful. All right, so I go through and, so take the expected value. I can factor out the n-1. And so I use the formula. And then once I get this, I go ahead and I start just doing, I start distributing. Well, the identity matrix doesn't change anything for multiplication. And then the J's are all ones. So a lot of stuff are going to cancel out. I mean, it's going to be really slick how this works out. Over here, I know this is a constant times J. This is a constant times J, and that's where I get this. And so the rest just comes from just knowing what's supposed to happen on every step of the way as I go. If you understand what these matrices are holding and their structure and the rows and columns, then you think about it for a moment and you see that this is all that we get. All right, then I notice that n minus n over n times n, this is going to be equal to 0. This cancels out, so I have the covariance of x and y times n minus 1 over n minus 1, which is the covariance of xy, which means that the expected value of our covariance estimate is unbiased, which should be reassuring. All right, rolling right along. Let's talk about the non-central chi-square distribution. So first and foremost, let's talk about the chi-square distribution. All right, so let's go ahead and say that z is an independent normal random variable. And we're going to say that the z vector is a standard normal multivariate normal. All right, well, let's go ahead and let's do this. I'm going to say that the sum of z squared is going to be distributed by chi-squared with n degrees of freedom. And I'm going to define chi-squared in that manner. And now I know that in stat theory, you go through, you take this and you build what this distribution actually looks like. For us, we're not going to sweat it so much. But just take the Casella and Berger book. It's required for this class as a textbook. So go ahead and review it if you're not familiar with how things piece out. All right, so if u is equal to the dot product between standard normal, independent random variables, then the expected value of u is n, and the variance of u is 2n, and our moment generating function is 1 over 2t to the power of n over 2. Now, all of this, if you're going to take the actuary exam P, you need to have this stuff memorized. This one will come up. All right, so let's do the proof. Well, what am I going to do? Here's u. I need to figure out what's going on with u. So, not me, with you. Get it? That's comedy gold. Okay, so I'm going to just go with what I define u to be. Now, I have a really slick formula if I have something in between them, right? So what I'm going to do, I'm going to put an I in between. Once I put that I in between, I can use that formula that we worked out previously. And so this expected value of this quadratic is just this. I'm just slapping in the I as I want it. Oh, and also, in this situation, our covariance is equal to I, and our expected value is equal to 0. So that simplifies a lot of stuff. So here, remember, we have A times sigma. And so I have I twice because I is up here. Now, using the formula, I've got mu I mu, but we know that mu is equal to 0, therefore it's going to cancel out. And so the trace is equal to n. Boom, we've got it. Now, for the moment generating function, what we're going to do is I'm going to use theorem 5.2b, and it's just a plug and chug. I know that the moment generating function of a quadratic is equal to something that looks like this. All I'm doing is I'm just tapping it in, tap, 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 plug and chug. And I see that, the i's, multiply just be I. I see the i's multiply to be I. This I inverse is just I. And then I have the 0 vector for mu, which means that this is going to just be equal to 0 up top. Exponent of 0 means I have 1. Remember, anything to the power of 0 is 1. All right, so all of this junk, this E business, it's out of here. And I'm left with this. Okay, well, remember, that's a determinant. Okay, so I have to take a determinant, but that's the determinant of a diagonal matrix. It means it's easy peasy lemon squeezy. And so I just take the determinant like I would normally, just like you would in undergraduate matrix algebra, and boom, we got it. Now for the variance, we're just going to use theorem 5.2c, and I just grab it, plug and chug. Remember, sigma is I, A is I, mu is equal to 0, and all this junk is 0 because mu is equal to 0. This is just I, and you know the trace of I is just n because I add ones to itself repeatedly, and there's a 2, so it's 2n. Boom, we got it. All right, note, if y is normally distributed and each y has a different mean, they're independent. So we'll go ahead and say that y, the vector y, is normally distributed with the vector mu and covariance I, so they're independent. Remember, multivariate normal, covariance of 0 and independent are the same thing, special situation. All right, something to realize is that the sum of squares, which is the dot product, is not chi-square distributed unless I have a mu of 0. It's important. Mean of 0 is important if I want to use the regular out-of-the-box chi-square distribution. Here, this doesn't apply because we don't have a mean of 0 necessarily. Now, if I change this up so that I'm subtracting off the mean each time, and I take the dot product, or the 2 norm, 2 norm squared, then yes, that is chi-square distributed because subtracting off the mean gives me a mean of 0. All right, if we go ahead and let's consider the situation where we're taking the sum of squared terms where we do not have a constant mean of 0. Like the means can all be different, but we have independence. Then what's going to happen is that we're going to say that V is non-central chi-square distributed. Okay, and we're going to denote that as chi-squared n and then lambda. Now this is different than the lambda we saw before. This is not an eigenvalue. This is a parameter. So something that we do with mathematics, we reuse stuff. And here we're reusing lambda because there's only so many letters in the Greek alphabet. So if you go into education, they change something very slightly and they make a whole new term for it. They never recycle words at all. In math, we do something completely different and we give it a different name, so you have to figure it out. There's advantages and disadvantages both ways. It's just part of getting familiar with your field. Okay, so what we're going to do when I'm dealing with non-central chi-square distribution, we're going to say that lambda is 1/2 times the sum of squared means. All right, and so that's 1/2 times the mean vector dot product with itself. And so lambda is a non-centrality parameter and it is non-negative. It's greater than or equal to 0. Otherwise, this would not make sense for us. Okay, so proposition. If y is distributed with a mean vector not necessarily equal to 0, independent and standard deviation equal to 1, then the expected value of the sum of y squares will always be greater than or equal to the expected value of y minus mean squared and then adding up. Okay, how do we prove this? Well, I mean, this is very similar to, remember when you like do the proof to work out that x bar minimizes the sum of squared deviation. I mean, basically it's the same thing. We have this particular formula. The expected value of y squared is the variance of y plus the mean of y squared. And so, and that just comes from that slick compact formula for variance. All I do is just go ahead, plug and chug, and I get it. Start plugging and chugging, and I see that I get some crap left over. And that shows me that it has, so this expected value is equal to n. This expected value is n plus 2 lambda. Because of that 2 lambda, unless lambda is equal to 0, we're going to have inequality. All right, now, if V is non-central chi-squared in degrees of freedom, non-centrality parameter of lambda, then the expected value of V is n plus 2 lambda, which we just showed. The variance of V is 2n plus 8 lambda. And here is the moment generating function. Okay, so The expected value is given a moment ago. Go scroll up a little bit if you want to see it. Now for the MGF, what I'm going to do, remember V is equal to the sum of squared Y's. All right, that's the dot product of Y. All right, well, if I look at this, it's okay for me to slap an I in between there, right? Once I slap an I in there, then I'm like, hey, that's a quadratic form. Now, I remember, hey, we've got independence. Independence means that sigma is a diagonal matrix. Furthermore, we said that the variance was equal to 1, therefore the sigma is equal to the I matrix. All right, so now what I'm going to do, I'm going to take the formula that we've used several times at this point, replace A with I, replace sigma with I, and mu is going to stay the same. So I just go in and I just start plugging it in all the way across. The I's are going to reduce down to just one I. I is idempotent. That's idempotent. Now I is its own inverse, and multiplying by I doesn't do anything, so this is going to disappear. All right, so now this is getting a lot cleaner. And let's see. Okay, so now I take a look at this, and I'm going to go ahead and change this just a little bit. So it's like I'm factoring out the 1 minus 2t, and I realize that that's going to be 1 over 1 minus 2t. Now I see that I've got I and I, so I can factor out an I, right? I, Captain. So when I factor out the I realize that I'm going to get a scalar. I can factor out that scalar, and so I get that to here. Now here, that just comes from these three terms. And so I know that this is going to be the dot product of the means, which, if I remember correctly from the definition of lambda, that's just going to be lambda. Now over here, remember that I have the identity matrix, and I have 1 minus 2t, and I'm taking a determinant. So this part on the inside, ignoring the exponent for a moment, this is going to be 1 minus 2t to the power of n, taking the determinant of a diagonal matrix. Now, once I go ahead and say exponent to negative 1/2, it becomes n over 2, but on the bottom because of that negative sign. And so boom, we've got this. Now, I want to take a variance. Now, all this work was just to get the moment generating function, which is fine and dandy, but I still want to compute the variance. So what I'm going to do, I'm going to take the log of the moment generating function. I'm going to remember the derivative of log moment generating functions has a special property. If I take the derivative once, set equal to 0, that gives me expected value. If I take the derivative twice and set t equal to 0, I get the variance, a very nice property. So let's go ahead and do that. So I take the logarithm, and so remember when I say log, I mean natural log. I don't mean base 10, none of that stupid junk. All right, well, the e was going to cancel out. Boom, that's nice. And here, when I take a log of a fraction, and I have 1 up top, remember the exponent comes out front, all that business. And so this simplifies down nicely. So now what I'm going to do, I'm just going to take a second derivative. Oh, sorry, here, this is where I'm at. I take a derivative, I get this. And if I plug in 0, you'll see that I get the value I was looking for previously. If I take the derivative again, I get this. When I plug in 0, I get exactly what I'm looking for of 8 lambda plus 2n. So here we've computed the expected value 2 ways, and then we computed the variance just 1 way, which isn't too shabby. All right, so now here, this is just talking about the additive property of chi-square distributions. And so if v sub I is non-central chi-square distribution with n sub I degrees of freedom and lambda I non-centrality parameter, and we have independence, that's important, then the sum of the v's is going to be a chi-square distribution where the degrees of freedom is the sum of the degrees of freedom. The non-centrality parameter is the sum of the non-centrality parameters. All right, so then if we have this, if I have a non-centrality parameter of 0, I'm talking about regular old chi-square distribution, and we have independence, then the sum of chi-square distributions, I just add up the degrees of freedom to get me the distribution, which should feel like a review from your stat theory course. All right, that's all I've got for you. Take care and goodbye.